Okay, let's continue. And I now will take my hat of chair of DecisionCAMP off, and I would talk on behalf of one of the popular decision intelligence platform known as OpenRules. And I am a chief technology of this company. And today I want to concentrate on so-called domain-specific business languages for different decisioning systems. And I selected one of the most complex domain known as scheduling and resource allocation. And I tried to approach this problem because it's quite complex, usually very complex decision-making problems. And you saw explanations yesterday by Helmut Simonis, what kind of problems we face, how serious they are, and how they usually require PhD level people to implement. And this always was being quite experienced in both area, in rule engines, in constraint engines. I always wonder, how can we bring power of constraint solvers to business user? Is it possible? And I actually spent even some essential time in university, and we even built standard today known as GSR 331 that provides Java API for constraint programming. But we have several initiatives. In last 15 years, we did some work in this direction, and you know that KU Leuven has CDMN, it's constraint programming, constraint programming inside DMN. This is another attempt to do it, but still we don't see common use of constraint solvers, powerful constraint solvers in this decision intelligence environment. It's always isolated problem. And so maybe it's not possible for business people to represent these problems. But I hope after today's presentation, you will see a more optimistic answer that it is possible. And I will demonstrate you on very particular examples how a business person can represent quite complex logical problems, scheduling problems, resource allocation problems. And I want to announce today a new product. No, we call it Rule Scheduler. And this product can be considered as a new incarnation of the old but great tool ILAC scheduler that was introduced in 1994 by great French company ILAC. And I was lucky to work with its creators, outstanding French computer scientists Jean-François Pouget and Claude Lepape. And I successfully, personally, and our company, OpenRules, or its predecessor company, we used ILAC products for many real-world scheduling problems for major U.S. corporations. But still, we were expert in low-level programming tools. We had to know these tools, and it was out of reach for business people. And over the years, ILAC scheduler was replaced with a low-level API. It gives programmers much more power than high-level scheduler, and in a way, it disappeared. So we decided with Rule Scheduler to revive major ILAC scheduler ideas, making them available to business users, not only to programmers, and who don't have a background. And very important, we want to put this in context of regular decision intelligence systems. It could be, we did it for OpenRules, but we open sourced everything. So basically, other people can take the same tool. It's everything with all sources open and incorporating other tools that currently used. So I will go to real demonstration. So when we're talking about resource allocation, scheduling concept, actually, conceptually, everything not as difficult as it sounds. If you think about scheduling, you have uh, only three major business concepts. You have schedule, and schedule have start time, end time, that usually called horizon, and the schedule can consist of multiple activities, and the activities can use multiple resources. And you saw examples in Helmut's presentation yesterday, and he did a very good job explaining this. And I just want to tell you that the rule scheduler brings this to the level of business interface, and still, and how it does this, it allows people to use traditional decision tables. It's single hit, multi-hit tables that support iterations that can be deployed in as RESTful services on any cloud. It can use debugger already included in this environment. It can use different deployment and other mechanism that already well presented in different decision intelligence tools. The only thing what we need to find the way to define the activity and resources. Then we need to find the way to present different temporal constraints. And when I say temporal constraints, it's relationship between different activity. For example, if you can have constraint like carpentry starts after masonry, or you can tell that ceiling starts after masonry, and all these possible combinations of different operators here could be defined. Starts after, starts 20 minutes late, starts after end, starts 5 minutes after start another activities, etc. All possible temporal constraints can be represented here, but they business constraints. That's what is important. And when you have resources, you can have multiple type of resources, and you just need to define requirements constraints. For example, you can say that each activity requires a worker, and worker is a resource, and this is resource reusable resource. After it's free, it can be used again. Or you can say that each activity requires $1,000. In this case, we're talking about budget, and budget is a consumable resource. And all this business logic concept could be presented in the rule scheduler. And what is also important, like in general with constraint solvers, you never concentrate on, or you almost never concentrate on solving. You concentrate on problem definition. That's why by its but very nature of constraint programming, it's always declarative system. And last year I presented the same general approach to all types of constraint problems, and we demonstrated, well, that time we implemented regular decision tables with different constraints, and we introduced in irregular tables, we allowed people to introduce special columns and special methods, and these methods in general way is they start with a prefix solver, but rule scheduler special columns start with prefix scheduler. And there are two big benefits of this. I just mentioned declarative decision modeling, so we concentrate on what instead of how, and also it empower our traditional DMN-like decision models with ability to represent and solve quite complex optimization problems. So, what we should do to represent problem with rule scheduler. Actually, we need to define only two tables. One table define for problem definition, another table for solve, called for problem solving. And here is example of such table for some problems here. as you can see, define actually defines different schedule, defines all activities, define all resources. It can post precedence constraints between activities, and it can post resource constraints from activities to resources. And this is the end of problem definition. And the problem solving, you should specify. If it's optimization problem, you can optionally specify objective. If not, you can find one feasible solution. And then you can use different predefined methods. It could be scheduler solve, scheduler minimize. And when problem is solved, you also want to save solution back to your business glossary, to business concept, to that actually will go from JSON request to JSON response and would be incorporated in standard decision modeling way with decision-making application. So I want to use examples, and you need to be patient because I'm going to show you all details from business perspective, and hopefully they're not so difficult. So I will use two main problems. One of them called house constructions, and we can use, when we construct house, we can use different jobs and different resources. I also decided to add oven scheduling. It's very, very simple problem to compare with what Helmut presented yesterday, but still it demonstrates business view of representation of such problems. And so let's start with these problems, and I will start with very simple problems, and we will keep adding more complexity as we go. So the first problem is a pure scheduling problem. And so we want to construct a house, and here is a list of activities for constructing the house. Masonry. After masonry, we can do carpentry. After carpentry, we can do roofing, windows, facade, gardening, but you can see all these relationships, and you can see all activities or all jobs, and all jobs have fixed duration. And the final step of these activities is moving in, and our objective is to move in as soon as possible. So this is quite simple scheduling problems without any resources, and how we can represent this problem in rule scheduler. So we can go here and start with very traditional way. I will use OpenRules specific implementation, and in OpenRules it's still DMN-like, but it has some specific features. For example, we do have explicit glossary defined. Each table usually has in the left top corner special keyword like glossary or decision test or decision data or decision table or single hit, multi-hit decision tables. But important thing here for glossary, it has two business concepts. One of them generic concept, and we can call it house construction, and we have concept of job. And each job has name, has duration, and this is our input information, and we want for each job to find the scheduling start for each job. So we put it in a red color because it's our output of our system. And you can see that house constructions refers to array of jobs, and this is type of this is array of these jobs defined here. So this is quite intuitive glossary, but before we go to problem solving and representation, we always should follow test-driven decision modeling. And here we have our test data. We put test data in the table of type decision data, and it has only two columns here, a job name, and we listed here all our jobs, and here's jobs durations. And now we can create different tests. So for example, here we can use just very simple one test, and we can tell jobs in here in house, these jobs should use these jobs defined here in this array. Horizon, this is end of schedule or maximum number of days. Let's say it's 30 days. And what we expect, we just made the approximate evaluation and think, can you do it in 17 days? If not, we will see mismatch, and the solver will tell us what the best solver can do, scheduler in this case. And so now we defined our table for problem definition. And this table it has 3 steps. Define schedule, this object, define activities, all these activities, and post constraints between these activities, because we don't have resources, so it would be only temporal constraints. So our first step, using predefined column, scheduler define. You can see prefix always scheduler, and then we use some words. It's basically right now it's just few columns to learn, but so it's more like oriented to business. And we will call this internal objects plan, for example, or schedule. But we will use here the second method is always what we want to do. We want to define schedule that starts at day 0 and ends and day defined as horizon in our test data. And so this is a regular business variables, and we just use them as this. And our second step is defined activities. And this is quite interesting. For each activity, we will, the same column, scheduler defined, can be used differently with different ways of different parameters. But second column contains methods, new activity. So we create new activity, and this activity, this is duration of this activity in one parameter, and name of this activity would be the same as defined in job name. So this is the definition we covered second step, and now we need to go to post temporal constraints. And temporal constraints were defined on this picture. We can create another decision table because we want to split. We can use one table, but we rather split separation of concerns. We create another decision table, and this decision table, it's a multi-hit decision table, and it doesn't have conditions, so it will execute all these what we usually call rules. In this case, it's just simple action, and this action called scheduler post, and you can see methods is activity, operator, activity. First parameter defines activity, third parameter activity, and relationship between them would be defined in second parameter. And we put here the sign just greater than, but you can write activity instead of this operator. You can write starts after, or you can write if you have more complex, for example, starts 5 minutes after, or it could be a lot of different parameters. But this in our the situation, they all activity starts after, or we can use the sign more, and we will create 14 constraints here to represent this relationship, just posting them. And I just want to stress again, I hope it's not so difficult for business person to map this picture to this table. And more than that, they will actually can concentrate on some business concept, strictly more or equal, or so starts at the same time, for example, you can put here more or equal, etc. And now, when this table completes our problem definition, and now we need to switch to problem resolution. And problem resolution, as I said, we can set objective, or even without anything, we could write schedule find solution, and it will find one feasible solution. But I would define here schedule set objective, and I put this in separate column, and I just can tell what is my objective. I want to moving in to start as soon as possible. So this would be my scheduler objective. And to solve the problem, I have table, standard table solve. It sets objective using this table, and it tells scheduler minimize this objective. Whatever objective is, minimize this. And because it defines everything in context of decision modeling, I can show this in our graphical environment. I can go through debug, execute, see what's the current state of each variable. But for simplicity, I just can run it. I can tell run this decision table, this decision model. So my model is completed. And when I run it, in reality, on the background, it would, our rule solver, our rule engine now is not just only rule engine, we call it decision engine, and it has three subcomponents, rule engine, rule solver, and machine learning. Rule owner inside. So now it would be, it will, because of this definition of this problem, it will switch automatically to to underlying constraint solver. And by the way, you can, because we use this JSR 331 standard, you can configure different solvers, and there are plenty of them, more than at least 20. They participate in different competition, and we just selected one of them. But we can, with one change in a POM file, you can switch between different solvers. But so we're using one of the solvers, I even don't remember which one. And when we, whatever was default, we executed this solution, and it's from first attempt, it found optimal solution. And it tells us that you can move in on day number 17, and you can see it took 123 milliseconds to find the solution. Okay, and when solution found, I actually have one more solver assign solution. This is this method maps whatever was defined by solver to business concept, and then you can use it in your JSON output, and that's how it's defined. And hopefully this was very simple. Of course, we can represent this graphically on some Gantt charts, but as a summary, I want you to remember only a few things. We have new columns: scheduler define, scheduler post, scheduler set objective, and scheduler minimize. Actually, for most problems, scheduling resource allocation problems, this is 4 columns will be sufficient, but each of them can use different methods inside. And that's why we have variable number of parameters, because of each method can have multiple parameters. And I will show you in next examples. So let's go to next example, and now we want to add resources. So let's assume that every job requires a worker. And if it requires one worker, each worker can perform only one task at a time. So we cannot schedule 2 activities at the same time if they use the same worker, right? So probably it would be more difficult to do general case that it could be one worker. So we can add to our test cases number of workers. If so, first test will have, we will try to solve this problem with one worker. What if we have 2 workers? Probably we can do much better. And by the way, this is expected results. For one worker, we expect to get to move in at with on day 28. With 2 workers, we expect on 18 day, and with 3 workers, we again can back to the fastest move in solutions. So this is our expectations. Now we will see what we can do in reality. First of all, because we defined in our test case number of workers, we need to add this number of workers to our glossary. So our decision model would understand what does it mean, number of workers. If we forget, it will immediately complain, especially graphically it looks nice, so that the number of workers not defined, and you need to add it to glossary. And so this is the business part of this. Now we go to constraint part. And what is worker? Worker is a recoverable resource, and it has capacity in this situation 1. And what we want to do, we want to add this worker. So I will go to the same table define schedule where we defined previously schedule. And now I can add here new resource, and we will call this not worker, but workers. And these workers, this is new resource, type of this resource recoverable, and capacity of this resource depends on how many workers we have. So we can put here number of workers, and now we can post constraints. Each job requires 1 worker. How to do it? We go again to scheduler post, But in this case, we will use new methods, and there are not too many of them. It's less than 10 methods. But they all predefined. And by the way, I will show in the end that we can define new methods quite easily. So this rule scheduler quite extendable. But so I will use methods. Activity requires resources, but this table will be applied in the loop. It will iterate for all jobs inside jobs, and for each job, it will say this current job, using job name for this current job, requires resource workers, and each job requires only one worker. If it requires two, it would be different problem, but you can put here number two, and this iteration, this decision table with iteration over jobs can post all constraints. So people who familiar with decision modeling, they would immediately feel that this is quite natural representation, and the only thing they have to learn what methods available and how to apply it. At least we do have practical experience when we show some people from movie industry, for example. It was another problem, and it was quite easy for them to understand. And now, to finalize this decision model with workers, we just need to inform our method defines that please also post resource constraints here. And when it posts resource constraints, we add it here. We just click again, execute this table, and we will got this. We got three tests, right? So for tests with number of one worker, we can move only on day 28. But this is expected. It's quite harsh requirements to use this worker, and it will calculate this. But when we go to second test with two workers, as expected, we will get start time in 18, day 18, and for three workers, we will go back to optimal start time, but we have plenty of workers. Okay, that sounds nice, but what happens in reality, probably you would not be satisfied with this, and you will have extra constraints. So let's look on this problem when instead of workers, we need to pay, for example, some building company, we need to pay 1,000 per day. We don't deal with workers right now. We just need to pay for each job requires 1,000 per day. But initially, let's say we had 13,000, and bank promised us another 16,000, but only after half of construction was completed. So how to represent or how to modify previous problems, for example, pure scheduling problems with these budget constraints. So we can define in our, let's start with test data, pure business concept. We're not talking about anything about constraints yet. And we can define here that we will define variable budget per activity per day is 1,000. So we're writing this like in plain English, you can see with all spaces. And then we will define, we need this initial budget 13,000. We need additional budget 16,000. And we need to add these three variables to our glossary just to be able to read this data from this test data. And by the way, instead of Excel test data, we can use JSON. I will show you if we have time how it works. And now we need to define this new constraints budget and post the proper constraints. And but in business terms. So what is budget? Budget is so-called consumable resource. It doesn't recover after use, right? If we paid this 1,000 and we had the first day we pay 1,000, for example, for masonry, so we instead of 13,000, we will have only 12,000 left to be used. After this, it never recovers. And so what we will do is the same table, define schedule. After definition of schedule, we will define new resource budget. And this is naturally using methods new resource. Type of resource is consumable, and maximal capacity of this resource is initial budget plus additional budgets. You can see here we use just regular field expressions from DMN, and we just can freely write any formulas here. Here just simple sum, but so you can use any formulas here because it's available in the general product. And then to post constraint that about budget, we need to say that this initial budget constraints that we have only 13,000 between beginning and the middle of our house construction process. So we can post here, and you can see another message, resource capacity max. It what it does, it says here that resource budgets from 0 to horizon divided by 2, it's the middle of our horizon. You can see another use of field expressions and just half of horizon. And use maximal capacity only 13,000, whatever defined in the variable initial budget. And so this is one simple constraint. And now we need to state that each job requires 1,000 per day. How to do it? We go to another decision table, and this table would be executed as many times as many jobs we have inside jobs. This is our iteration loop. For each job in jobs, execute this table, and what to do, use one column scheduler post and use another method. Previously, it was activity requires workers. If you remember, activity requires resources. Here, activity consumes resources. All these nice words, requires, consumes, they were introduced by Alex scheduler, and I loved them that time, and I was upset when the majority of solvers lost them, but we recover them. Here, activity consumes resource, and which this current activity, whatever is in this loop with this job name, it consumes resource budget, and how much? It's 1,000 per day as defined in our test data, and or in real data if we use JSON. And then we just need to put these two constraints in our two tables what we just added to our define methods, and just click execute. And when you execute, you will get immediately interesting results. Now, this is a solution. We can do this work with this limited budget. We can move in only on day 20. But you can also notice that its solution number was number 4, not number 1. So because it's interesting that we looked for optimal solution, and this optimal solution actually went through. First solution was day 23, then second solution 22, 21, and finally it get to solution 20, and it proved that this is optimal solution. Under these constraints, you cannot find better solution. And let's keep going. Oh, if you want to represent this graphically, it's a little bit more difficult, but you can see here on this picture that masonry takes 7 days. In first day, it will take 1,000 of resource, second day, 2,000, 3,000, etc. But after day 6, this money disappears. You cannot use them anymore. And you can see how solver reshuffle different activities differently. Now you can, carpentry actually move to day 14, and plumbing starts early on day 10, and it went through all this possible combination to resolve this problem. So while problem already was not trivial, it was probably manually, it's very difficult to resolve this problem, but it's already quite nicely presented and could be extended. And if you have, instead of many more activities, it still would be able to resolve these problems. And now, I naturally wanted to, why we talking about workers or budget? What if we have both constraints? We have workers and budget. So let's take our previous workers and try to add budget constraints on top of them. So what we will do, we will add here in our test data, we always start with tests, because tests dictate us what we want to do. So we did have some number of workers, 1, 2, or 3. There's 3 different tests here. And we just defined our budget constraints with 1,000 per day, initial budget, additional budgets. We just added these 3 columns to our test data, and we in define schedule, we just need to add one more column, workers we defined previously, budget, as we did in pure budgeting problem with consumable resource. And when it's done, we adding these tables in our common problem definition table define, and we can execute it. And when we execute it, we hit, it wasn't surprising for me, but we hit immediate, or that problem was over constrained. When you use one worker and 1,000, solver tried hard and it could not find solution. And actually, we got lucky that it could not find solution so fast, because one of the most difficult part of constraint programming to prove that there are no solutions and to point to over constraint, what exactly caused this over constraint and how to relax constraints, all these issues much more serious. But when we go to 2 workers, solver was able to find quickly solution for that. It's with 2 workers and budget constraints, you can move in day 23, and with 3 workers, you can move even in day 20. But you can see it again took 4 attempts to solve this problem. And finally, I want to show you even more difficult problems that still could be implemented here. And let's say that we have different resources with different skills. For example, and different resources can have also different costs. So, for example, in this table, we can define, if we add another column to our jobs table, we can say that masonry that still requires 7 days could be done by Joe or Jack. Carpentry, Joe or Jim. And plumbing can be done only by Jack. So there are no choices here. And if you look on gardening, we can use one of these 3 resources. So this is another definition how to use alternative resources. And and here in this table, you can see that each resource has different costs. And in this situation, for example, Joe costs 300 per day, Jack 230. Probably he is more preferable to use as much as possible, etc. And how to define this? And first we introduced here concept of worker. This is business concept before thinking about the constraints. It's a business concept worker. Worker has name, daily cost. Worker has capacity. It could be limited capacity, but in this case, it's 1, of course, in our test. We add all workers in our house problems, and here we have array of workers, so we probably would need to iterate through this array. And for each job, we also added here possible workers who can do these jobs. So it's an array of strings with name of these people, Jim or Joe. So they would be in this array. And also we added here not only moving in day for the entire schedule, but we also added total cost. How much would it cost us? So when we can define these workers as alternative resources, we write here worker name, a new resource, and this is the type of this resource is disjunctive. Yes, yesterday Helmut mentioned about disjunctive resources. So only one, this resource could be used only once, and if each worker is disjunctive resource because it can be used by one and only one job at a time. And when we want to add job worker constraints, we again use this table inside loop over jobs, and we use new methods here. Activity requires one of alternative resources. So you can see we want to make it as business friendly as possible, and we tell which activity for each current job, activity with current job name can require one of these possible workers resources, only one of them. Activity requires one of alternative resources. And how to calculate cost? Oh, we just had this user-friendly methods, total resource cost, and it takes one parameter here, 2 parameters, worker names and worker daily costs. And so it means we will be able to calculate this cost if we add this to our problem definition. And after adding these tables to initial pure scheduling problems without resources, when we added this, we will quickly find out that, great, we still can move in on day 17. However, calculated cost was 5,320. So after this, we started to think maybe we should change our optimization objective from move in as soon as possible to the smallest cost. How to do it? Oh, we do have this separate table set objective. So now instead of using this table, move in as soon as possible, we will set objective total cost. And if total cost is defined here, we can run without any other changes, we can run the same decision model. And when we run this decision model, it would be quite interesting that it will find solution with cost 5,160. And so, but you can see now day, instead of moving on day 17, we're moving 3 days later. And but our cost is smaller. How much smaller? It's still a question. Do you want to spend extra money to move in as soon as possible or not? Actually, you can define more sophisticated objective. You can give so each objective different weights, and you can ask solver to minimize a scalar product of these objective variables. And this also all possible, but for sake of time, I will move forward. And I want to show you this example. And this example is a trivial example from yesterday's Helmut's problem. He had to deal with very complex array of production power ovens, multiple ovens, and they all busy. It was, and he beautifully describes these problems. But I will take very, very simple problem. Let's imagine that you have you're running company and you have one oven, and this oven fire batches of bricks. And you received 5 orders, and here's this order. This order requires 2 batches to be fired for 1 day. This order B requires 1 batch to be fired for 4 days, and the biggest one is 2 batches for 4 days. And so basically, and this is my availability of my oven. Probably it already runs previous order, so it's not everything available. For example, on this day, it cannot do anything, but it still has empty spaces here. So if you don't do anything, such trivial problems, you can just graphically try to place these pieces here, and Kit can do it. But let's do it and represent this problem in our decision modeling environment. So how would it look like? First of all, I will again define my glossary. And my glossary now has, I will call general glossary oven. Oven has maximal capacity, but also oven includes multiple orders. And orders, I define orders by name, order duration, order size, number of batches, and we want to, this our output, we want to know when to start each order. And we also have object availability to represent this current availability of this oven, and this from to and available capacity. For example, in day from 2 to 3, capacity is equal 0. Here capacity 3, here capacity 1. So let's see how we can present this. We can say we can use regular tables, and we can say that these orders we present orders, order size, order duration, and we can present availability from to, exactly as I just mentioned, and we can define our test case. For example, altogether we have 11 days. Oven maximal capacity is 3, and then availability that limits our capacity. This defined in this array, and orders defined in array of orders. So this test data as business test data. And now I want to define my problem. So define problem, it means very similar what we did before. We will use table define schedule. It defines our schedule. In this case, we can call it oven or plan, but let's say firing bricks, you can write here, is defined from 0 to 11, and we will use new resource oven, and oven is recoverable resource. That's always very important business concept. It has some maximal capacity, in this case 3, and then we can post constraint that about orders, so it will create new activities for each order in array of orders. Then we will post constraints, availability constraints, and here we use resource capacity max. We already saw this method. So, for example, oven from this time to this time, and these elements available in our glossaries, business concepts, have this limited capacity. So it will run over array of oven availability. And then to post constraints, finally, we just have to tell that activity requires resource. We iterate over all orders, and we tell that each order requires this resource, and this is order size. So basically, this is quite, I hope it is intuitive for business people as well. And for people, subject matter experts who understand this problem, at least they can read it, they can understand this. And then I can run this problem, and I almost immediately will receive the same solutions that you can find manually. Okay, hopefully this examples gives you idea how scheduler works, and it gives business user ability to represent quite complex problems, scheduling, resource allocation problems, but it also means that we put this representation in already working context of decision intelligent tool. And it means, for example, I can run this problem in graphical IDE. So I can just, I would not go to this demonstration of now, but I can show you, we can build the decision requirement diagram automatically. Then I can click here and debug it. I can execute rule one by one and see all variables as you go through all these steps. But this is not for oven, this is for alternative resource picture. And then I can, this probably I do have few minutes to show you. I can actually, if I go to just without graphics, I have here, and if you download the rule solver, you also will get all these examples. And schedule alternative resource mean cost. I can just, if I click run a local server, it will automatically deploy my solver, this decision model as a RESTful service. It generates in JSON file, it generates my test converting from Excel, collects everything in form of JSON. And then you can run this JSON. Let me just run it here. And if this is a real Postman, after it gave me my endpoint URL, here I'm copy my JSON file, and when I click send, it should execute. But what is interesting now, I'm in quite complex optimization problem. It should go, it takes 12 seconds to execute. What I've seen, probably first time it takes more. Okay, it's count on 12, it should produce results. But because now it's trying to find optimal solution, it finds several solutions, but it still will take more time to find optimal solution. Why it takes more time? Okay, it found a solution, and now it took 34 seconds. If I click second time, it will take only 12 seconds. But what is important, let me go back to slide, it will show you all results, including moving in date, including total cost in JSON format, and now you return this JSON response to your decision-making application. So basically, with rule scheduler, problems, scheduling, resource allocation problems become available to people who define business decision models. They are in their native decision modeling environment, like OpenRules or like any other tool like FICA or TriSaTech, for example, if they implement similar interface. And what is So as I mentioned, all sources publicly available, and we don't. By the way, we also, for very complex problems, we have easily we can switch to low-level Java API, and if necessary, you can write new constraints and new methods and make them available to business users. And but of course, this requires knowledge of Java, and so as a summary, we can solve scheduling and resource allocation problems in a familiar DMN-like decision modeling environment. Okay, I hopefully, yeah, it's enough time. So thank you, and any questions? Okay, Helmut.
Yeah, very nice. A completely different way of modeling and writing the constraint model. Obviously, in your setting where you have a rule engine and so on, this is actually quite a nice integration. One thing I'm a bit worried about is there doesn't seem to be a clear separation between the model and the data. I find for Minisync or OPL, this is actually a very nice thing where you have an abstract description of the model, and then you have the data that is given in a JSON file or some other format. Yeah. How would you comment on that question?
Oh, in reality, this is completely solved by a decision modeling environment. Data could be presented in any format. It can usually, the most in production environment, it comes traditionally from, if it's a RESTful service, from JSON format, but this JSON could come from a graphical interface or downloaded from database. It's kind of outside of decision model. It's another decision for applications that invokes the decision service in general. But we, in OpenRules, for example, we allow to represent data in different Excel tables, and we have quite powerful data representation. For this, it's kind of small database in Excel, with including primary keys, foreign keys, and it's possible to do. But even when you do this, it's convenient to do for business users to use Excel directly. Then when they click one button to deploy or test, they immediately can automatically generate JSON, and this JSON would be passed to IT team for integration. So there are no limits here, but the beauty of this approach is that it has nothing to do with rule scheduler or rule solver. It's just it's how particular decision modeling tool deals with data.
Okay, thank you.
Okay. More questions, please? Okay. If no questions, we can thank you very much. And I will stop this recording. And our